All right, so the through line of this chapter really is the notion that the physical states of matter, whether it's solid, liquid, or gas, is a direct function of those intermolecular forces. And also the physical properties of liquids and solids are also a function of those intermolecular forces. And so then it comes as no surprise that changing between those phases, solid to liquid or liquid to gas, etc., it should be thought of from a perspective of how those intermolecular forces are changing, right? So I've got all of the different types of physical state changes between substances. So we've got solid liquid, that's fusion or melting. We've got liquid solid, that's freezing. We've got liquid to gas, that's vaporization or boiling. We have condensation, which is gas back to liquid. We have sublimation, which is, these set are usually the ones that we don't think about as much. So solid directly to gas, that's like dry ice, CO2, going directly from the ice form all the way to gas, that's sublimation. And the opposite of that is even stranger, which is deposition. We don't see that quite as often, where it goes directly from gas to solid by skipping over that liquid state. So all of these states are a function of those intermolecular forces, their strength and their robustness, how long they can last. But it also should be noted, after we've talked about thermochemistry, that all of these have a delta G associated with it, meaning the transition from one physical state to the next also has a change in free energy of those physical states. Even though we're not talking about changes in bonds per se within a molecule, intramolecular, we're still talking about the changes in energies by the changes in intermolecular forces between one state to another state, whether that's solid to liquid, liquid solid, liquid gas, etc. So we need to think about these delta G's, and we need to invoke what we've already learned in accounting for different energies to be able to now include these physical states of change in our accounting process. So recall that one of the most popular and most important equations in all of general chemistry you'll ever learn is this notion that the change in free energy, or delta G, of one state to another is a function of two primary variables. One is the change in enthalpy, or delta H, which is really the heat flow, either heat going in or heat going out of the system. And what we thought about before was this delta H was bond making and bond breaking. So when you created or destroyed a new covalent bond, that was associated with the change in the enthalpy of the system. It's really no different here, except the bonds that are forming are bonds between molecules rather than within them. So this is the heat flow with respect to the intermolecular forces being made or broken in either physical state transition that we have over here. And then the delta S component here, the change in entropy, is really no different. Before we talked about whether it was the change in molecular randomness, and that's true here too, right? We already have an intuition for this, because when you have something in a solid form, it's locked up in this physical state where you've got all the molecules and they're completely immobilized in the crystalline lattice. That's a low entropy system. The universe doesn't like that, right? It takes energy to keep things ordered. If you traverse that to a liquid state, now those things, they're still close to each other, but they've got a lot more degree of flexibility and randomness in the system. And so we can think of delta S really in largely the same intuitive terms that we thought of it in previous chapters. Okay, so if we know that about the delta G, then we can think about this graphically, where we have, again, all of our 6 possible physical states of matter change that I have listed on the left that we've already covered. And then on the right, we've got this graphical illustration of increasing enthalpy, meaning increase in the heat of the system towards the positive direction. So delta H is positive up here, delta H is negative down here. And then we have the increase in entropy, or delta S, increasing in the positive direction on the right and decreasing down below. So in the graphical representation, we have the 3 physical states of any substance, and this is going to be true regardless of the substance. It could be water, it could be benzene, it could be ammonia, anything. So at the bottom we have the solid, right? And the solid has the lowest entropy, meaning it's got the least randomness, but it's also got the lowest enthalpy of the system. So think about, say, ice. So that's water in the solid form, right? All those water molecules are locked up in position, they're immobilized. So if we add energy to the system in the form of, say, heat, what we can do is traverse directly from solid to gas through the sublimation process, and in that case the delta H and the delta S are going to be greater than 0. I should write this equation up. So delta G equals delta H minus T delta S. So in that case, you remember, for a spontaneous process, we need delta G to be negative. In this first sublimation process, going from solid to gas, we've got a positive delta H, but we've also got a positive delta S. So these two things are competing with each other to determine whether or not this overall sublimation step is a net spontaneous process. We can think about the change in delta H, delta S intuitively for all of these other reactions, or all these other physical state changes, right? If we go from solid to liquid, which is this change over here, this is fusion or melting, heat goes into the system, right, because we need to break apart the intermolecular forces that are holding the ice together, the molecules of water and ice together. So that means delta H is positive again. It also means delta S is positive again. And so those again are competing energy values that ultimately dictate what type of, whether it's spontaneous or not. Vaporization, again, requires heat to break apart the liquid molecules, liquid water, to turn them into steam or gaseous molecules. That's going to create greater randomness in the system for a gas as opposed to a liquid. And then going in the opposite direction for like condensation, right? If you condense a liquid droplet from gas, that means heat is flowing out of that system, and the intermolecular forces then dominate. We also lose randomness of the system, and the same is true for freezing.